Today we are going to do the limit of a Riemann sum, and this is what leads us into the integral, which is the third and final major topic of calculus. So hopefully you have downloaded this, the calculus guided note-taking sheet, whatever this is, on limits of Riemann sums. That's posted on the Google Classroom. And I want to do a back and forth with this. The way I normally do this in class is I will have people get me your answer for number 1 and then we'll talk about it. Then give me your answer for number 2 and then we'll talk about it. And so that's what we want to sort of try and do here is I'm going to ask you about number 1. You pause the video and see if you can solve it. And then check back with the video and see if you got the same solution that I got, and just do them one step at a time, back and forth with the videos like that. If you're really ambitious, try and do the whole thing independently, but good luck with that. But ambitious people might want to do that. All right, so here we go. We're going to create a right-hand Riemann sum approximation for the area under the curve f of x equals x squared over the interval 0 to 2 using n rectangles. So this is the same area that we've been looking at over and over again, x squared over 0 to 2. And but this time I'm not saying how many rectangles there are. So why are we doing that? Because we've gotten to understand by this point, using Riemann sums, that the area, the true area under the curve, is approximately equal to the sum from I equals 1 to n of the individual areas of the rectangles a sub I. So each of these rectangles is a sub I. I've drawn this with sort of a non-specified number of rectangles. So we're going to call this, as usual, I think I've been calling them R1, but a sub 1, a sub 2, a sub 3 for area. All right, and then right here is going to be our a sub n, so this one's a sub n minus 1. So this one that is unnamed, we often call that a sub I, the ith area rectangle. So the ith rectangle. All right, and what we're going to do is sort of by analyzing that unspecified rectangle, we're going to be really analyzing them all. By analyzing an unspecified number of rectangles, we're going to get a handle on any number of rectangles, and that's sort of our goal here. All right, so then the other thing that we're going to remember is in all of these, that sum from I equals 1 to n of a sub I, that is itself equal to the sum from I equals 1 to n, I'm laughing at my terrible sigma, of f of x sub I delta x. Right? Because if we think of these as the x sub 0, x1, x2, all right, then this one here is x sub I, and that means that the height of the rectangle is f of x sub I, and the width of the rectangle is what we've been calling delta x. All right. So, and then other things that we have with regard to that delta x is we know that delta x is equal to b minus a over n, where b and a are the endpoints of the interval we're considering. All right, so that's what we're after. Now, in particular, since this is we're doing a right-hand one first, so we're going to do actually a right-hand sum. So we're also going to remember that the real area that we're looking for, the true area, is actually less than this sum. So the true area is less than the sum from I equals 1 to n of f of x sub I delta x, because a right-hand sum is used on an increasing function. All right, so this is what we're going to get. We could call an upper bound on the area, the true area that we're looking for. All right, so the first thing we're going to do, step 1 here. So don't be misled by, I have these like Roman numeral headings that give, this is a general strategy of what we're trying to do. We're trying to create this formula, and these steps are how you're going to do that. Number 1, remembering that n is a variable, find an expression for delta x in terms of n. So you should pause the video and see if you can do that. All right, so now I'm assuming that you paused the video and have attempted number 1. It's weird talking when nobody's there. Anyway, delta x. So what is delta x? We want an expression for delta x, right? So we know from here delta x is b minus a over n. We know that the beginning of the interval is a and the end of the interval is b. So we have 2 minus 0 over n, so 2 over n. So delta x is going to be 2 over n, no matter how many rectangles I have. Delta x is 2 over n. So see, I've already got a piece of this. And the idea is I want to be able to get everything in terms of n so that I can apply a limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. If I can make that make sense, then I would have the exact area. That would equal A. All right, but does it make sense? I don't know. That's what we're here to find out. Well, all right, I know, but we're gonna explain why. So our second step, so now we're ready to do step 2. It says create a sequence of expressions in terms of n that represent the x sub I values, okay? X sub 1, x sub 2, x sub 3, x sub 4. What are they? What are x sub 1, x sub 2, x sub 3, x sub 4 in terms of n? All right, you pause and figure that out. All right, so I'm assuming you are back now. So what you want to focus on is that the delta x is equal to 2 over n every time. So x sub 1 is just 2 over x. And x sub 2, well, it's going to be 2. I got 2 delta x's, right? Delta x and then delta x. So 2 delta x's, so 2 times 2 over x is 4 over x. All right, and then x sub 3, I'm going to have 3 delta x's, so 6 over x, 8 over x. And that's how that, oh, I'm sorry, these are n's, darn it. These are n's. 2 over n, right? 4 over n, 6 over n, 8 over n, all right? That's what that, what the sequence of the x sub i's are, right? Because the delta x is 2 over n, delta x is 2 over n, so 2 over n, 4 over n, 6 over n, 8 over n. All right, that is our number 2. All right, so now you're gonna attempt number 3, and I'll present that in the next video.